I used to message you all the time with that. It's like, back up I focus on I'll have my phone off. Oh, yeah. Why? Just start screaming at yourself in the air.
Okay, 2 o'clock. Let's get going here. Am I mistaken? Is this the beginning of the 5th week? It is, right? The 5th week. 5th of 8. Yeah, we only have, yeah, okay. So we're officially halfway. All right, so last class we were discussing, we had kind of switched gears. We were talking about finding the volumes below surfaces and between surfaces. And we had talked about type 1 regions was what we ended with. So we know that if we have a surface and we want to find the volume below it, and I guess we could call it like the shadow of the surface on the ground is a rectangle, that's the easiest, I guess, double integral we can have. And then we said if the shadow on the ground is something like that, so if our domain on the ground is something where we can restrict our x between 2 constants and our y's between 2 functions of x, then we have this thing called a type 1 region. And the integral is a little bit different. The double integral is different because you can't switch the order of integration anymore. You're forced to do it in that order. And we did one example, and then we were going to get going on the second one here. So here's our second example. Just find the volume under z equals x squared plus y squared on the region bounded by y equals 2x and y equals x squared. So the way we started this in class last time is we started by drawing the domain, the region that's on the ground. So I'm going to start here with our domain. This domain lives in the xy plane. Y equals 2x is going to be a line that goes through the origin. And then y equals x squared is a parabola that also goes through the origin. Kind of exaggerating it there. And we are trying to find the volume underneath some surface on this region bounded by these two. So is it clear the region that we're talking about has to be bounded by both of these curves? Is it clear? Okay, so it's this closed region right here. Right? So any other region that you would look at would not be bounded by both of those curves. So our region has to somehow close off. So when you look at that region, we have to determine what type region it is, and I'm going to draw it again over here. So it's type 1, right? Obviously, because we're still talking about type 1, but let's just make sure we understand why. The idea is that any time we go into this region, if we were to draw like an infinitesimal little slice in here, that the x values will be trapped between 2 constants. So no matter where I slide this rectangle, left or right, the x values are always between 2 constants. And the y values, these will change, right? The top and the bottom of this rectangle will change as I move throughout this region, left and right. But the top will always be dictated by which function? Which function is that one, and then which one is this one? So what is my top bound?
Your top bound is going to be 2x.
Yeah, the 2x. Now going back to the notes, let me show you that type 1 region. We call that top one g sub 2 of x call the bottom one g sub 1 of x. So I'm going to use that same notation here. So this is our g sub 2 of x is equal to 2x, and then the bottom one is g sub 1 of x, and this is x squared. So we should be able to start setting up the integral. What's the one thing we still haven't determined that we'll need to figure out? We know our bounds on y, right? Our y bounds are between x squared and 2x, right? Our y's are always between those two. But what still have we not resolved? The x bounds, right? So our bounds on x have to be between two constants, and we need to determine those. And we can do this either visually, like inspecting it, or we can do it by setting the two equations equal to one another, which is, I guess, the way I'll do it. So let me find the intersections. So the intersection is going to be setting the two functions equal to one another, and then solving that. I actually solved that today in my college algebra class. We were talking about being very careful and not dividing both sides by x, that you have to move everything over to one side, and then factor. So this is where we get our two solutions, 0 and 2, right? So 2 here and 0 here. All right. So now what we do is we set up the double integral. All right? So the volume of this, I'll call it V, will be the double integral. So in our first integrand, or first integral sign here, it's going to be our limits of integration will be our restrictions on x. So for us, it'll be 0 to 2. And then our inside integral will be our restrictions on y, which are from x squared to 2x, sorry. And then the integrand. So what is it that we're putting in here? What is our integrand? It's the z, right? It's z written as a function of x and y. So it's just x squared plus y squared. And now we need the dy dx thing. So what order are we going here? What's the inner one? dy is going to go first, and then dx. And since this is our first one, and there was a whole 4th of July break and everything, let's go ahead and just take this one all the way. Looks like it's not going to be too difficult to plug things in. So working with this inner integral, do that one first. So I'm taking the antiderivative of both of these terms with respect to y. So the antiderivative of x squared with respect to y is? With respect to y, right? So yeah, so we're just x squared y, right? Because we're treating x squared like a constant. So the antiderivative of that should just be the constant times y. Danny, yes? Now this one will be your 1/3 y cubed. So plus 1/3 y cubed. And now we're going to put the evaluation bar in here. And remember I said last class, this is where you want to know what this is going to replace. And these are going to plug in for our y's, right? So it might be helpful to put y equals x squared here and y equals 2x here. Then we'll figure out what all that is. Then after we're done, we're going to do our outer integral. So this now becomes integral 0 to 2. And I'm just going to write this the way that I like to do it. I know with the fundamental theorem of calculus, the evaluation theorem, we're going to plug 2x in, and then whatever we get there we'll put here, and then we'll subtract from that whatever we get when we plug in x squared. So let's do this. 2x right here for y, right? Which is going to give me 2x cubed. So 2x cubed. And then plus 1/3. And then I'm putting 2x in here and cubing it. So when I cube 2x, get 8x cubed. And I have to do the same thing, but now I'm going to do x squared in. So x squared here and x squared there. So we should have For that first one, x to the fourth, right? X squared squared, or x squared times x squared, so x to the fourth. And then another plus 1/3, and now we're doing x squared, but we're cubing it, which is x to the sixth. All right, let's clean this up before we do any more integration. All right, I don't really need the brackets, but I'll put them here. Looks like we have some like terms here, right? These are both x cubes. So this is 2x cubed, this is 8/3. So what is that if we combine that? 14/3 x cubed. So 14/3 x cubed. Then I'm going to wind up subtracting an x to the fourth and subtracting a 1/3 x to the sixth dx. And that's not too terrible, right? We can just use power rule on each of those. So we'll do that. This is equal to, let's see here, antiderivative of that. I'm just going to write down 14/3, and now the antiderivative x to the third is 1/4 x to the fourth, and then minus 1/5 x to the fifth, and then this one's going to be minus 1/3 times 1/7 x to the seventh, and we're evaluating at the two different places. Let's see, 0 and 2, and this is x is going to be 0, x is 2. Let me see, I'm going to clean this up. 2 goes here, 7. That I can't clean up. So let's do 2 in here. So what happens if I put 2 here? What's that, 16? Right? So 16 divided by 2 is 8 times 7, 56 over 3. So 56/3. And then minus, now 1/5, and then we're going to do 2 to the 5th power, which is 32, so 32/5. And then minus, let's see, 2 to the 7th, 128 over 21. And then we need to take all that and subtract from it whatever we get when we plug in 0, but thank goodness that's just 0. And now you need, what, a common denominator? Yeah. What's a good common denominator here? Let's see. Probably 105, I'm thinking. Is that the smallest one? 105?
Yeah.
105. Well, we can get a decimal answer, but we can also get an exact answer, right? So I'm just going to say dot dot. I think this is, yeah. Okay, so, I mean, you get the basic idea?
Yeah.
Yes?
How'd you get 7?
Right here? This was 4 and this was 14, so I just reduced one each by a factor of 2. So 2 goes into 4, 2 goes into 14, 7 times, right? All right, let's see, do I have this one worked out? Let's see here. Yeah, so there's the region on the ground, and there's our surface. Just put that solid in there. So we found the volume of that solid right there. So you can find the volume of some pretty strange looking shapes this way, right? All right. All right, so that's 2 examples of type 1 regions. What do you think comes next? Type 2 regions, right? So what are type 2 regions? Well, a type 2 region is everything basically reversed. So instead of having your x's between 2 constants, the region that you have, your y's are between 2 constants, and your x's are between two functions of y. So this goes back to like Cal 2. You have this idea of functions of x versus functions of y. So functions of x are functions that pass the vertical line test. But if you have something that goes like this, that's not a function of x, but that could be looked at as a function of y. So it actually passes the horizontal line test. So we're looking at this case right here. What if your region looks something like that? Well, the only thing that changes is your order of integration. You're now going to do dx first before dy, and your limits of integration are going to be, your constants are on the y this time, and your functions are on the inner integral, which is your restrictions on x. So I think it's just going to flow right over from the type 1. We just need to make sure we can get our head around, when we are given the problem, recognizing whether or not it's type 1 or 2. So let's look at this one. So find the double integral over d of xy with respect to area. So this basically means find the volume under that surface on this domain where the region is the one bounded by these two curves. So let's write those down first. This is a line, right? This is a line. And then y squared equals 2x plus 6. This is a parabola, but it's not your traditional parabola that opens up or down. Because the y is the thing being squared, this parabola opens either left or right. Right? So this will not be a function of x because you cannot solve for y and have a single answer, right? If I try and solve this for y, I'm going to have square root, and I'm going to have plus or minus, so I'm going to have two different functions. So I cannot look at this as a type 1. Let's try and draw this. Let's go with the, let's see if I've got some decent colors here. That one's not bad. Okay, that one's good. All right, so let's do this one first. All right, so we can all graph that, right? Okay, y-intercept of -1 comes down, has a slope of 1. So that is your y equals x minus 1. This line can be looked at as a function of x, can't it? Or a function of y. It can be looked at both ways. As a function of x, we solve for y. As a function of y, we solve for x. So we would solve this for x and have it written as a function of y. Now the other one, how do I graph that one? You want to try and isolate x here? Okay, so let's make this the red one here. So if we isolate x, solve for x, you would get x equals, so go ahead and let's just do that algebraically, maybe in our heads. What do we have? 1/2 y squared minus 3. So if it were written this way, I trust that everyone could graph this. This is a parabola. It opens up because this is positive. It's been moved down 3, and it's actually spread out a little bit because this number is smaller than 1. Okay, but because it's written this way, as a function of y, this parabola is going to open to the right or to the left? To the right. So it's going to go like this, but it's been moved, let's see, -3 this time for us means which way? To the left 3, so it's like this, and it's been spread open because it's 1/2. So it's basically like rough picture without a calculator, without graphing utility is something like that. All right, that's essentially what we're looking at. So when you look at this, I want to make sure everyone is clear that this is not a type 1. So let me act like I'm trying to treat this as a type 1. Type 1 means that my x is stuck between two constants and my y is between two functions of x. So imagine drawing a vertical little rectangular slice here. Is the top and bottom of this thing two different functions right now? Like my top is this curve, right? My bottom is this curve. So it appears like right here it's okay, right? If I move this to the right, it's still okay. But it's when I get over here, when I get to this point, if my rectangle was over here, what's the problem? The top and bottom are coming from the same curve, right? And that's where we run into an issue. So we can't really look at it with these vertical slices. We instead have to look at it with horizontal slices. If we slice this way, then now is my y-coordinate, are the y-coordinates of this rectangle always between two constants? So as I move this, will my y's stay between two things? And hopefully you can see from that intersection over and then this intersection point over, there are my two restrictions for y. And now the question is the right side and left side of this rectangle always going to be two different functions? So no matter where I move this rectangle, no matter where it is in here, as I let y move, right, this rectangle, is it always the blue on the right and the red on the left? The whole time, right? So in the previous type 1, it was the top one minus the bottom one, right? That was kind of like on our double integral. We had the restriction on a and b, and then here was our g1 of x, and here was our g2 of x. This was the top one, this was the bottom one. With this, it's going to be, the one on the right is like the top was, and the one on the left is like the bottom. All right? So I think we're ready. No, we're not ready. What do we still need? Have we written both of these curves as functions of y? Yeah, this one, I still need to work with that. I need to solve that for x, right? This is x equals y plus 1. And now we're going to look at this as being a function of y. And this one up there, I do have written as a function of y, don't I? Okay, so we're going to call the blue one h2 of y. And we're going to call the red one h1 of y. And we need our restrictions on y now, right? So right now I know that my x's are bound between, let's see, the red one, which is this one. It's the one on the left, and then the right one is y plus 1. But I need my restrictions on y, which I'm going to get from the intersection again, right? But when I set them equal to one another, when I do this intersection, I'm going to set this equal to this. So that way my equation will be in terms of y, right? So I have 1/2 y squared minus 3 equals y plus 1. And this is a quadratic, so we can solve this. I'm just going to multiply everything by 2 to clear out the fractions. And get everything over to one side. Minus 8. And that factors, fortunately for us, but if it didn't, we could use quadratic formula or something. We should get, yeah, so minus 2 and y is positive 4. So I'm just going to trust that you could set that, factor it and set it equal to 0, get your solutions. Okay, so that means this was 4 up here. And this one was -2 down here, right? So we're going to go from -2 up to 4. We're going to let our rectangle move through there. We have our right bound and our left bound, which are these two. So our y is between -2 and 4. Okay, we have everything we need, right? Just set up the double integral and then start cranking it out. I think we may not take this one all the way. And I told you last class that on your final, I will have you take some of the integrals all the way, but there will come a point in time where it's too time consuming, all right, to do all that. So we're going to just set it up. So the double integral over d of xy with respect to area should be, okay, limits of integration on my outer integral will be our constants. The inner integral will be these. And then our integrand is the integrand here, and then the dA is written how? So are we going dy dx here, or are we doing dx dy? Dx dy. And again, the way to remember that is the outer, right, is our restrictions on y. The inner are restrictions on x. So we would first integrate that with respect to x, right? And then after we do that, we plug in, replace all our x's with this and this. And then we integrate that with respect to y, and then replace all our y's with our constants. Now, y'all said y'all were fans of Wolfram Alpha, yes? Y'all know Wolfram? I mean, there's other things out there now. Wolfram Alpha is still the... What's that other one? There's another one that shows all the steps and stuff. Symbolab, yeah, that's a good one. I'm going to go to Wolfram Alpha. I'm going to integrate x times y from, wait, hold on. Let's just see how smart this is. Integrate this dx first, right? From, where are we going? 0.5y squared minus 3 to y plus 1. Let's see if it can interpret that. So I'm having it do the inner integral for me. That look like it? Right? That look like it? And it's giving me the answer right here, right? So let's see if I can wrap that with another integral. So I'm going to put this in parentheses. Okay, and I'm going to integrate that with respect to what? dy, right? From -2 to 4. You think it can do all this? Ooh, look at that. Y'all are very lucky you live in this day and age. And this is why I am not a huge fan of actually making you compute this stuff, because the technology is there to do the integration. The part that requires the human still is the setting it up. Setting up the integral. Maybe not for a problem like this, but later on when we're like, you know, we have a word problem, we're trying to solve it, then we have to turn it into the math first, then you know, then you can let the computer take over. But yeah, so the answer should be 36. We won't go through the work. Okay, so here's a slightly different problem. Find the volume of the tetrahedron bounded by this. What is that geometrically for us in this class? What is that? It's a plane, right? That's a plane equation. So we want to find the volume of a tetrahedron that has a plane as one of the boundaries. X equals 2y is another plane in three-dimensional space, right? X equals 0 is the YZ plane, so that's another plane, right? And then Z equals 0 is the XY plane. So you have basically the ground, right? That's Z equals 0. X equals 0 is this wall, right? Remember, this is x-axis, y-axis, Z. So we have the ground, we have this wall. We have X equals 2y, which is a plane that runs vertically, right? No. Where did I put all that stuff? Sorry. Oh, there they are. X equals 2y is a vertical plane, right? Because there's no z in here. So your z is free, so it's some sort of line like this. Or not line, a plane like this. So the ground, this plane, and then this plane does have some sort of pitch to it like this, right? It's not straight up or flat. So we've got this other plane that's somehow cutting through. So I'm guessing it's going to look something like this. Okay, we have, let's go with the plane up there. Where does that touch the axes? So where does it touch the x-axis? Where does this plane touch the x-axis? Well, when you're on the x-axis, y and z are 0, right? So touch it too?
Yeah.
So if this is x, this is y, this is z. We have at 2 here. And then where does it touch the y-axis? At 1. And where does it touch the z-axis? At 2. Right? So you can imagine like a plane cutting through like that. That's not the whole plane, but that's part of it, right? So we've got that plane. We've got the ground. That's z equals 0. We've got the back wall, the yz plane. That's x is 0, right? And the only thing we're missing is this piece, this right here, which I'll write it this way. Y equals 1/2 x. So I'm going to solve it for y. So y equals 1/2 x. That would cut through. That would cut through like something like this, somewhere in there. So one way you could kind of visualize that is, let's look at just the ground, just the xy plane. Y equals 1/2 x. That's y equals 1/2 x, right? That line goes in both directions. But if I plot that here, if x is 2, y is 1, I know that that line would come through like that. Do you all see that? Yeah. That's this picture on the ground. Do you all see it or not? Looking from the top, that's the origin, and then that's the point 2, 1. So our plane comes through here and slices through, goes back to that. What's in black is what we're trying to find the volume of. You all see that? Is there a question? No? Okay. Do y'all see it or not? Go ahead, speak.
How do you know which one it is? It's not the other one.
Which one? This one on this side?
Yeah.
Because the purple here is x is 0, right? Yeah. So this wall is here. There's no wall here, right? Yes? So we have the back wall here. That's x is 0. You have z is 0, which is the bottom. You have this slanted face, which is that equation. And then this one right here creates this cut right there. Yes or no? What do you think? I mean, okay, we're trying to find the volume of this. So how can we find the volume of that? Using a double integral. So do you see that as, can you see this as the volume below a surface over some region? Okay, so what is the surface that you're looking down below here? It's this equation right here. It's this surface, right? That surface is going to be the top of this thing. And if you look straight down, then I was trying to do this without any aids here, but you know, this, oh, whoa, can't see that. we're kind of looking at it from kind of like this perspective right here. It's kind of the perspective we're looking at it from. You all see that? So this surface right here is that plane equation. If we look from straight on top, maybe not. Can you see that that plane straight down onto the ground creates, I gotta sneeze. Excuse me. Thank you, thank you. Okay, do y'all see that that top surface straight down creates our domain on the ground? Okay. So this is going to be able to be done with the double integral. Let's try and, now that we've kind of drawn it out and reasoned through it a little bit, let's start with our domain, all right? We've already started it there, but let's start with our domain. And also, you know what, let's get this. Let's solve that for z. Z is 2 minus x minus 2y. So this is our surface. This is our function of two variables that we are going to be looking below down to the ground. So that's our surface. Our domain is in the xy plane. So we got to talk about this little shadow in here, this little piece down here. We got to talk about that. So some of the points we know are there. The origin, right? The origin is there. This point 0, 1 is here. And then I had drawn this a second ago. We had that line that came out like this, right? And then we also know that there's a line that goes like this, and that's the one that goes from here to here, right? So we are looking at this right here. This is our region right there. And so what type of region is that? Is that a type 1 or a type 2?
I see it as a type 2.
See it as type 2?
Type 1, actually.
You could look at it both ways, actually, here. It could be both ways. But I think a type 1 is easier.
Yeah.
And the reason why type 1 is easier is because with type 1, if I draw rectangles, no matter where I place these rectangles, that curve's on top, this curve's on bottom, right? If you switch it and you go the other direction with rectangles that way, then it's going to switch. The left and the right functions are going to switch halfway through. So you could do it that way, but you have to break it into two double integrals. So I think we're going to go, let's go type 1 here. And since it's type 1, that means that I'm going to have some restrictions on x that are between two constants and restrictions on y that are going to be between two functions of x. So can you tell what the constants are? 0, 1. I mean, that was just by my drawing, though, right? Are we pretty confident that these hit each other? What is this line right here? What is this one? What's the equation of this line? That's y equals half x, right? That's that one. What's the equation of this line? We never actually figured it out, right? We just drew it off of this thing. We picked these 2 points and then drew the line through there. So we could get it by coming up here and letting z be 0. Or we could just look at this, like back college algebra, like what's the y-intercept? Right? So the y-intercept of this is 1, and what's the slope? So down 1 over 2, so negative 1/2 x, like that. So these are our two functions of x. This one will be the g2 of x, and this one would be the g1 of x. Does that make sense?
Yes.
And do they hit each other at 1, 1?
Yeah.
So if I plug in 1 here, I should get the same thing as if I plug in 1 in here. 1 there, I get a half. 1 here, I get negative 1/2 plus 1, I get a half. So yeah, they hit each other, right? Okay. Did I say 1, 1? I think I said 1, 1. I did say 1, 1. I said, did they hit each other at 1, 1? That's not what I meant to say. Do they hit each other when x is 1, is what I meant to say. So our bounds on x are from 0 to 1, right? So x goes from 0 to 1, and then our y is the lower function here, and then up to our upper function, which is 1/2 x. And, right? Oh, yeah, wait, hold on. I got these backwards, don't I? I have these backwards. This one's G1. So what would happen if I did that wrong? See how you have those backwards? What do you think that's going to do to the, these are backwards. It's going to give us the answer, but negative. So you'll get the same, you'll get the correct numerical value, but it'll be off by a sign. So the lower one is this one, which is that, 1/2 x. And the upper one is this one, negative 1/2 x plus 1. So the last thing to do is set up the double integral. You see what I mean by, like, this is the part that the human needs to do, right? And then the computer can do the double integral for us. Okay, so we're going to go double integral. All right, this is type 1, so I'm going to go restrictions on x first, and then restrictions on y. My integrand is going to be the surface that I'm looking below, which is that plane equation solved for z. And my order of integration is dy first, and then dx. And then we could have the computer do that for us, or we could do it by hand, right? You can suffer through that during your homework. You can do that, all that nasty computation to get that practice. And this would become a little messy because when you integrate with respect to y, you'll have 2y minus xy minus y squared. And so when you plug in, that's going to need to be squared, and things are just, it's going to get, algebraically, it's not fun, but you know, it is what it is. All right, how do y'all feel about that one? A little bit more involved with the tetrahedron, with a little bit more going on there? Okay. I think the question for you becomes, you know, do you have it set up properly? Like, is this the correct region? Let's take a look at this one. Find this. So here, just giving you the double integral right away. You know what? Let's cheat. Let's cheat. Let's go to Wolfram alpha again. And oops, I need the function up there. Okay, so we're going to go to Wolfram alpha. We're going to try and do this. Right. So I'm going to have it do this step at a time. So let's do the inner integral first. The inner integral, take all that off, and we're integrating sine of y squared, right? Sine of y squared, we're doing this with respect to y, and we're going from x to 1. Y'all agree? Yeah. Okay, let's see what happens. Excuse me. I'm allergic to y'all. That's not a good sign. That's very interesting. What is that? It's square root of pi over 2 times s of the square root of 2 over pi minus s of the square root of 2 over pi x. What is capital S? Oh, it's this. It's the Frenzel S integral. Well, what's the Frenzel S integral?
Question.
Good question, right? So anytime you ever go to Mathematica, or Wolfram Alpha, and you start seeing stuff like this, that means you are now pushing the limits of what it can do, all right? So these are like error functions. These are things that are picking up. It can do it within a certain error, all right? Now, what happens if I wrap this up with, let me do the outer integral with it. See, the issue, well, let me do it. Dx from, what is it? I erased it. Was it 0 to 1? Oh, well, it didn't have any problem with that. Okay, so what happened here is that when you did this original integral, or when we did this original integral, the limits of integration involve variable expressions, right? From x to 1 and 0 to 1. So since our limits of integration involve variables, it's trying to give me an antiderivative and this should be a function, right? So this is an indefinite integral because it's still indefinite in the sense that we don't know the value of x, so we can't calculate this. When we do that, and then we go and we integrate it again, and we put this 0, 1 here, now it's a definite answer. So it can give us the numerical solution. So I guess my best way to kind of make you understand this is, remember in Cal 2 you had power series, right? So a power series allows you to integrate things that you can't normally do. Like one of the classic examples is to integrate e raised to the x squared. So if you type in e to the x squared, a classic example from Cal 2, you're going to get 1/2 square root of pi ERFI. This, what is that? That is the imaginary error function. Right? So it can't do it. It gives you, there's no closed form of the antiderivative of that. Now, if you scroll down, it will say, well, wait a minute, hold on. I can give you a series expansion of that. Okay, I can give you the series expansion of that answer. And so when you go and you throw in here one more thing, like from 0 to 1, it's going to crank that answer out because now it can actually go into the power series and evaluate the power series. That's exactly what happened on this one. We did the inner one, and it was kind of like us trying to do e to the x squared. And as soon as we put the 0 to 1 on the outside, it said, okay, now I can use a series to do this. All right. So will you at least agree with me that that does not look like something that we are going to want to try and do on our own? Because that initial integration of sine of y squared is not something anyone here is going to be able to do. Right? If I say go integrate sine of y squared with respect to y, everyone's going to be pretty much stuck at that point. Don't go try it. You're not going to get it. It's not something that you learn in Cal 2 to do. All right? And so, what is this? Why do I have this in the notes? What do I have written there? Order might matter. So let's take a look at this from a different perspective. This is actually an integral where the region we're integrating over could be looked at as a type 1. This is type 1 because I'm going dy then dx, right? So this is telling me that my x's are bound between what? 0 and 1, and my y's are bounded between x and 1, right? Now, can you draw that region? Let's draw that region. So my y has to be bigger than or equal to x. So that right there is just the diagonal, isn't it? So that looks like this. And then this right here, y equals 1, is just a flat line through 1. Right, here's 1. So it's like this. And x is 1 is here. So we were doing this right here, right? That region, that's what we were doing. And they were treating it like a type 1 region. Let's just, for the sake of doing it, switch it to a type 2. See what happens. What is this written as a type 2 region? So if this is y equals x, if I go to a type 2, this time my rectangles are going this way. What are my restrictions on y? As a type 2, this was as a type 1. So as a type 2, this time my y is between two constants and my x is between two functions of y. So my y is between what here? 0 and 1. Okay, so that didn't change. But what about my x is between these two functions of y. So what is this bottom or left piece? That's x equals 0, so that's 0. And then this right here is this solved for x. So x equals y, right? So does this even help us at all? Like, what is this doing? What are we doing? What does this do for us? Let's rewrite it. This new double integral should now be, what? Still 0 to 1. But instead of x to 1, it's now, what? 0 to y. So that doesn't really seem to help. This is the part right here. Because what are we going to integrate with respect to first? X this time. Which makes all of this a constant. All right? So now let's integrate that with respect to x. See, do you see what happened here? Let's see. We should be able to do this. Okay, so let's go here. This is integral 0 to 1. The inner integral, the antiderivative of sine of y squared with respect to x is just x times sine of y squared. And we're evaluating that where? At what equals what? X equals 0 up to x equals y. So remember, because our inner integral is with respect to x, so these are our restrictions on x, these are our restrictions on y. So we're going to take the antiderivative with respect to x, then plug in this y for x and 0 for x. And then when we're done, we'll integrate that with respect to y. So, all right, so what happens when we replace this x with y? We get y sine of y squared. And then minus, when we plug in 0 here, we get nothing, right? So now we're stuck with this. But this we can do. Because this is basic u substitution now. Because the derivative of y squared is out here. We're off a little bit, but it's there. Wasn't there in this form. We try and integrate that with respect to y. We don't have the y out there. Right? So this, I'm not going to go through all the work, but this should be 1/2, negative 1/2 cosine of y squared. Let's just double check that. What's the derivative of this? So what's the derivative of that? Negative sine of y squared?
Yes.
Times 2y,
Yeah.
chain rule.
Yeah.
So if I hit that with a negative 1/2, I should get back to this. All right, so this is the antiderivative of this. But we're going to evaluate that at y equals 0 to 1. So if you plug in 1 here, well, cosine of 1 is something, right? 1 squared. So this can be negative 1/2 cosine of 1. And then minus, plug in 0. What do you get when you plug in 0? Cosine of 0 is 1, right? So you just get minus 1/2 here. Yeah, so this is minus 1/2 cosine of 1 plus 1/2. Which if we do that on our calculator, I'm willing to bet that if you do that, I've got rid of it. Oh well. Well, I'm going to bet that it's the same thing. So I don't remember what the answer was. Did you do that? No? Okay. Maybe I'll do this. 0.229? I think you're right. So if I integrate and then integrate again, what was it, sine of y squared dy from, help me out here, what was the original problem? X to 1? X to 1, and then we integrate that one with respect to x from 0 to 1. Yeah. 0.22, yeah, 0.229849, which is what you got from that? Yeah. So that shows you that when you're looking at a double integral, if it's given to you, that if it's a tough integral, maybe you can look at the region, maybe it can be switched into a different type region, and then maybe it'll go a little easier that way. Okay. I know that there's a problem like that on the final, but the instructions are switch the order of integration. That's all it says. So they give you that, and they tell you switch the order of integration. So that means you need to make this be dx, dy. You need to switch those, which means you need to go draw the region, switch it, make it the other type, and then do your new. All right, some properties of double integrals. Properties of double integrals. So there's some good news here. If you have some region D here that you're trying to integrate over, you can split it into two regions, D1 and D2. And if you want to know the double integral over the whole region, you can just do the double integral over each of the individual regions and then add the two answers together. Does that seem plausible, seem reasonable, I should say? Okay, so this is saying that's allowed, all right? All right, this one is so important, but it's going to be even more important as we proceed into triple integrals. So remember that if we're looking at a surface floating in the air here, this is D on the ground, right? Then the volume of everything below that is the double integral over D of that surface with respect to area, right? That's what we've walked into class kind of knowing this already. But what if I tell you that this function here is the constant one function? That means that this function is no longer this thing floating around. It is just a flat surface that is exactly 1 unit off the ground. Okay, so can you visualize that? It's just a flat surface, unit one, so flat plane, 1 unit high. Then the volume, okay, I shouldn't make this necessarily a rectangle. Wouldn't the volume of this thing be equivalent to the area of D?
Yeah. Yes.
Shouldn't it?
Yes.
So let me give you an example. Let's say we take a cylinder. Okay, what is the volume of a cylinder? Well, we can look in the back of the book. We see pi r squared h is the volume of a cylinder. So what this is, pi r squared is the area of that circle, isn't it? And then the h is the height. So what I'm saying is, what if h is 1? If h is 1, isn't the volume the same numerical value as the area of that circle? Now, they have different meanings. Like volume is a cubic unit and area is a square unit, but the numerical value will be exactly the same. That's what this is saying right here. If you ever take the volume under the constant 1 function over some region D, then you're going to always get the area of D. That's what you're going to get.